Far out in the frozen darkness drifts a world called Eris. It is a dwarf planet whose discovery forced us to rewrite the rules of our own solar system. This distant, icy sphere holds secrets that challenge everything we think we know about the planets in our cosmic neighborhood. By the end of this journey, you will know the 25 most profound mysteries that make Eris one of the most enigmatic places we have ever found. We will explore why its brilliant surface defies explanation and question if it could harbor a hidden ocean deep within. What does a world so distant and strange reveal about our own place in the cosmos? That single measurement, a tiny point of light from the Hubble Space Telescope, ignited a firestorm that reached every classroom on Earth. Astronomers had calculated Eris to be larger than Pluto, a fact that forced the International Astronomical Union to make a monumental decision. They created a new category, the dwarf planet, and reclassified Pluto, stripping it of its traditional planetary status. The debate was fierce and public, pitting scientific definition against cultural sentiment. Yet, this entire cosmic reshuffling rests on one critical uncertainty. We still do not know the precise size of Eris with absolute certainty. Initial estimates were based on its incredible brightness, but an object could appear bright for two reasons. It might be genuinely large, or its surface could be an exceptionally good reflector, like a cosmic mirror. Later observations from an occultation, when Eris passed in front of a distant star, suggested it might actually be slightly smaller than Pluto, though its greater mass makes it significantly denser. This leaves us with a profound puzzle. Did we demote Pluto based on a measurement that was just a little bit off? The very definition of our solar system hinges on the exact dimensions of this mysterious, distant world. A reminder that sometimes the smallest data points can force the biggest changes in our understanding. That brilliant reflectivity is more than just a visual marvel. It is a direct scientific contradiction. Eris shines brighter than freshly fallen snow, reflecting over 96% of the light that touches it. In the darkness of the Kuiper belt, it acts like a distant lighthouse beacon. Such extreme brightness implies a surface that is impossibly clean and young. Most objects in the solar system are darkened over eons by cosmic radiation and dust, slowly turning them a sooty gray. Yet Eris defies this aging process. Its surface is believed to be a shimmering blanket of nitrogen and methane ice, as bright as a mirror. How can such a pristine surface exist on a world that has been orbiting for billions of years? One theory suggests constant geological renewal. Imagine the ice cracking and shifting, with fresh material welling up from below to cover the old, darkened terrain. But this presents another puzzle. Eris is a small, frigid world, far from the sun's warmth. What internal energy source could possibly power this resurfacing? Could there be enough heat left from its formation, or from the slow radioactive decay of rocks deep inside its core, to drive such change? The surface of Eris is not just a passive shell. It is an active, dynamic puzzle, forcing us to question what tumultuous processes are hiding beneath that dazzling, frozen facade. That brilliant, mirror-like surface holds a deeper secret, one that appears and vanishes with the seasons. Eris follows an incredibly elongated path around the Sun, a journey that takes 557 Earth years to complete. For a brief period of this long orbit, it ventures close enough to the Sun's faint warmth for a miraculous transformation to occur. The intense cold that grips its surface, typically near -400 degrees Fahrenheit, might rise by just a few critical degrees. This tiny increase in temperature could be enough to trigger a spectacular event. The nitrogen and methane ice on the surface could sublimate, turning directly from a solid into a gas without ever becoming a liquid. For a short, glorious time, Eris might puff out a wispy, transient atmosphere. Imagine a cosmic flower blooming in the deep freeze, its delicate petals of gas unfurling for a fleeting moment before the world swings back into the darkness. Detecting this ghostly shroud is a monumental challenge for astronomers. The atmosphere would be incredibly thin, and by the time its faint signal travels across billions of miles to reach our telescopes, Eris could already be receding, its temporary sky collapsing back onto the surface as a fresh layer of glittering frost. This cycle of potential birth and death makes Eris an object that is not just distant, but fundamentally different from any world we know. Its very air is a temporary, seasonal mystery, a whisper of gas that comes and goes with the slowest of celestial breaths. Orbiting this brilliant, seasonal world is a silent partner, a moon named Dysnomia. This companion holds the key to one of Eris's most fundamental properties, its mass. Before Dysnomia was discovered, Eris was just a point of light. Astronomers could estimate its size from its brightness, but they had no way of knowing how much stuff it was actually made of. The discovery of its moon changed everything. By carefully tracking Dysnomia's slow, steady orbit around Eris, scientists could apply the laws of gravity to perform a cosmic weigh-in. They watched how the two bodies pulled on each other. A gravitational dance that revealed Eris is about 27% more massive than Pluto. This was a staggering revelation. It confirmed that Eris is not just a bright speck. It is an incredibly dense and substantial world, but Dysnomia itself is an enigma. Its orbit is nearly circular, which is unusual for such a distant system, and it is remarkably large for a moon of a dwarf planet. In fact, Dysnomia is estimated to be over 150 miles across, making the Eris system more like a double planet than a simple primary and moon. How did such a substantial moon form so far from the Sun? The leading theory suggests a cataclysmic birth, a colossal impact billions of years ago where a massive object slammed into a young Eris, blasting material into orbit that later coalesced into Dysnomia. This would make their story a frozen echo of our own Earth and Moon. Yet Dysnomia's composition remains a total mystery. Is it a chunk of Eris's own mantle, a captured rogue object from the Kuiper belt, or something else entirely? This moon is more than just a measuring tool. It is a relic from the solar system's most violent era, a silent witness to the chaos from which Eris itself was born. This strange gravitational dance between Eris and Dysnomia is set against a cosmic stage of incredible extremes. The path Eris carves through the solar system is unlike any other, a wildly eccentric and tilted orbit that speaks of a turbulent past. For most of its 557-year journey, it dwells in the profound outer darkness, but its orbit is not a neat circle. It is a long, drawn-out ellipse that takes it on a staggering journey. At its closest approach, Eris ventures to within 38 astronomical units of the Sun, a distance that still places it far beyond Neptune. But then it swings outward, receding to a breathtaking 97 astronomical units. To put that in perspective, at its most distant, Eris is nearly 100 times farther from the Sun than Earth is. This is not the sedate, predictable orbit of the inner planets. This is the path of an object that has been violently disturbed, a cosmic billiard ball sent careening by a powerful gravitational shove. What force could have possibly placed Eris on such a strange and lonely road? Astronomers suspect it was not a single event, but a slow, gravitational ballet with Neptune. As the giant planet migrated outward in the early solar system, its immense gravity may have steadily nudged Eris, pulling it into an orbital resonance that eventually flung it out into the frozen depths. But there is a more tantalizing possibility. The sheer degree of its orbital tilt suggests that Eris may have experienced a close encounter with another, as yet undiscovered, planetary body. Could a hidden world, a ghost planet lurking in the darkness, have grazed past Eris and sent it tumbling onto its present course? This peculiar orbit is more than just a trajectory. It is a fossil record of the solar system's chaotic youth, a clue that the ancient past was far more crowded and violent than we ever imagined. This overwhelming mass and brilliance make Eris a true giant among its neighbors, a king in a realm of icy pebbles. The Kuiper Belt is a vast disk of frozen remnants, but most of its inhabitants are small and dark. Eris stands apart, shining with an intensity that dwarfs nearly every other object out there. Why is this one world so different? Its sheer size and density suggest it formed under unique conditions, perhaps in a region of the early solar system that was far richer in building materials. One compelling theory proposes that Eris is not a native of its current neighborhood at all, but a stranded immigrant. In the chaotic first few 100 million years after the Sun ignited, the giant planets are thought to have migrated, their gravitational influence scattering countless objects across the solar system. Eris may have originated much closer to the Sun, in a more densely packed region near Neptune's orbit, where it could gorge on material and grow to its impressive size. A gravitational kick from Neptune, acting like a cosmic slingshot, could then have hurled it outward to its present lonely orbit. If this is true, Eris is not a typical Kuiper Belt object, but a relic from a different, more violent chapter. A planetary embryo that was exiled to the frozen edge of the solar system before it could grow any larger. Its presence there today forces us to ask, how many other giants are hiding in the darkness, and what stories of ancient migration do their orbits hold? That dense, massive core might be far more than just a collection of rock and ice. The incredible reflectivity of Eris points to a world that is geologically alive, actively refreshing its own surface to stay brilliantly white. But on a small world so far from the Sun, where could the energy for such renewal possibly come from? The answer may lie deep within, in the slow, steady decay of radioactive elements. Imagine the core of Eris as a natural nuclear reactor, packed with unstable atoms like uranium and thorium. Over billions of years, these elements release heat as they break down, providing a persistent internal warmth. This is not a fiery inferno, but a gentle, smoldering heat that could be enough to soften the ice mantle above it, allowing it to slowly churn and convect. This internal warmth creates a fascinating contrast with other icy worlds. Pluto, for instance, shows clear signs of recent geological activity, with vast glaciers and young mountain ranges, likely powered by the heat from its own radioactive core. But Eris is smaller and should have cooled faster. If it is still geologically active, its core must be exceptionally rich in these radioactive elements, a relic from the solar system's violent birth when such materials were scattered throughout the forming planets. This leads to an even more profound possibility. If enough heat is being generated deep within Eris, it could be sufficient to maintain a layer of liquid water beneath the thick, frozen crust. We are not talking about a global ocean like Earth's, but a deep, dark subsurface sea, isolated from the universe above by dozens of miles of ice. The presence of such an internal heat source transforms Eris from a simple frozen rock into a potential habitat, a world where the basic ingredients for life, liquid water and energy, might coexist in the perpetual night. Even that brilliant white surface holds a secret palette of subtle color. Enhanced telescopic observations have revealed that Eris is not a uniform, featureless ball of ice. Patches of its surface appear slightly reddish, while other areas shine with a purer, brighter white. These faint discolorations are more than just cosmetic quirks. They are direct clues to the chemical processes and violent history etched onto this distant world. The reddish tints are a classic signature of tholins, complex organic molecules that form when simple ices like methane are bombarded by cosmic radiation over millions of years. Imagine the surface of Eris as a vast natural laboratory. Solar winds and distant stellar radiation slowly cook the methane ice, breaking it apart and reassembling its components into these reddish, tar-like compounds. This process, called radiation darkening, should eventually turn the entire surface a dull brick red. So why is most of Eris still dazzlingly white? The presence of bright, white areas suggests that this darkening process is being actively counteracted. Fresh, clean ice must be regularly exposed, covering up the older, red-stained terrain. This could happen through constant geological activity, where internal heat pushes new ice to the surface, or through the slow sublimation and redeposition of frosts during its long seasonal cycle. Perhaps recent impacts have excavated pristine material from deep below the surface, creating brilliant new craters that temporarily outshine the ancient, darkened landscape. Each subtle hue on Eris tells a competing story of aging and renewal, a quiet battle between the relentless darkening of space and a hidden energy source fighting to keep this world impossibly bright. The persistence of methane on Eris presents a fundamental cosmic contradiction. Volatile compounds like methane ice are not expected to survive for billions of years on a world so small and distant. Closer to the Sun, on objects like Pluto, the tenuous warmth is enough to cause these ices to slowly sublimate into space, escaping the weak gravity and vanishing forever. Eris, however, defies this logic. Its surface remains coated in a glittering shell of methane, a substance that should have boiled away eons ago. So how does Eris cling to its fragile, frozen atmosphere? The answer likely lies in an environmental state of perpetual deep freeze, a condition so extreme it acts as a perfect natural refrigerator. Eris experiences some of the coldest surface temperatures in the entire solar system, routinely plunging near absolute zero. At these incredible lows, the vapor pressure of methane becomes almost non-existent. Essentially, the molecules lack the thermal energy to break their frozen bonds and escape. This process, known as cold trapping, keeps the methane locked in a solid state, frozen directly to the surface with an unbreakable grip. It is a far more effective trap than anywhere else we have observed. Yet this explanation only deepens the mystery of the surface's brilliant reflectivity. If the methane is so permanently frozen, how does it stay so clean and bright? The very process that preserves it should also allow radiation to slowly darken it over time. This suggests that Eris is not a simple, static ice ball. It might possess a unique thermal cycle or internal structure that allows for subtle surface refreshment even within its state of ultimate cold. The methane is both a prisoner and a puzzle, its continued existence hinting at a world of delicate and unexpected balances in the outer darkness. This internal heat source could be seeking an escape, potentially erupting in slow, frozen fury from the surface. The concept of cryovolcanism transforms Eris from a static ball of ice into a world of potential geological drama. Unlike the fiery volcanoes of Earth that spew molten rock, a cryovolcano would erupt with a chilled slurry of water, ammonia, or methane ices. Imagine a slow-moving glacier of slush, forced upward from a deep, subsurface ocean or a warm layer of convecting ice, oozing out across the landscape in a freezing flood. This process could be the key to the planet's impossible brightness. A fresh eruption of clean water ice, laced with ammonia that acts as a powerful antifreeze, would spread a brilliant, reflective coating over the older, radiation-darkened terrain. Each eruption would be a resurfacing event, painting over the scars of cosmic age with a new, gleaming layer. The energy required for such activity is immense, yet Eris seems to possess it. The decay of radioactive elements in its core could provide just enough persistent warmth to keep parts of its icy mantle soft and mobile, creating the pressure needed to drive this slushy material to the surface. Visualize the hypothetical scene: a vast, slow-motion geyser of icy crystals freezing solid in the vacuum of space, falling back to the ground as a blanket of pure white snow. This cyclical process of eruption and deposition would continuously maintain Eris as the brilliant mirror we observe, a world actively sculpting its own appearance from the inside out. Could we one day find the frozen calderas and flow patterns of these icy volcanoes etched into its surface, the silent testament to a hidden, churning heart? The very spin of Eris is a fundamental mystery we have yet to fully solve. While we know it rotates, the precise length of its day remains a subject of intense study. Determining this simple fact from billions of miles away is a monumental challenge. The rotation rate of a world directly shapes its destiny, influencing everything from its global form to the hidden workings of its interior. A rapid spin could force Eris into an oblong, football-like shape, its material stretched outward by centrifugal force. A slower, more stately rotation would allow it to settle into a nearly perfect sphere under the pull of its own gravity. Current estimates hint at a rotation period longer than one Earth day, but the exact number is still elusive. This unknown has profound implications. A slow spin would mean long, lingering days and nights on its surface, allowing temperatures to plummet to even more extreme lows during the endless darkness. This could deepen the cold traps that keep its methane frozen solid. Conversely, a faster rotation would create a more uniform global temperature, mixing the climate and potentially affecting the stability of any temporary atmosphere. When we compare Eris to other dwarf planets, the puzzle deepens. Haumea, for instance, spins so rapidly it is visibly distorted into an ellipsoid. Pluto rotates at a more leisurely pace, with a day lasting about 6 Earth days. Where does Eris fit on this spectrum? Its rotation speed is a direct clue to its history. A fast spin could be the lasting signature of a giant impact, the same violent event that may have created its moon Dysnomia. A slower spin suggests a more tranquil formation, relatively untouched by such cosmic violence. Until we pin down the rhythm of its day, we cannot fully understand the forces that have shaped this distant world from within. The subtle gravitational pull of this distant world may be actively carving its signature into the surrounding cosmic neighborhood. Astronomers are investigating a compelling hypothesis that Eris, despite its vast distance, possesses enough mass to act as a gravitational sculptor. Its immense gravity could be shepherding the orbits of smaller, icy objects in the Kuiper belt, clearing a faint zone or creating a discernible pattern in the distribution of debris around it. This would be similar to how a planet like Neptune has swept its orbital path clear, though on a much smaller and more subtle scale. Detecting such an effect from Earth, however, is a monumental challenge. The Kuiper belt is an enormous and sparsely populated region, and the gravitational influence of a dwarf planet is incredibly weak across such distances. It would be like trying to hear a single soft whisper in a roaring hurricane. Confirming this requires mapping the precise orbits of countless tiny, dark objects over many years, looking for any consistent gap or grouping that points directly back to Eris's location. If this gravitational fingerprint is real, it would elevate Eris from a solitary wanderer to a central force in its own tiny corner of the solar system, a hidden puppeteer gently tugging on the strings of its smaller companions. What other invisible patterns might its gravity be weaving in the darkness? This question of origin strikes at the very identity of Eris. Is it a true native of the Kuiper belt, or is it an immigrant from a different part of our solar system, or even a visitor from another star entirely? The answer lies in its strange path and its chemical makeup, clues that tell two different stories. One theory posits that Eris formed right where it is, coalescing from the primordial cloud of ice and rock that constitutes the Kuiper belt. In this scenario, it would be a local king, the largest product of its immediate environment. Yet this idea struggles to explain its incredible size and mass. The region of the Kuiper belt where Eris now resides is sparse, making it difficult for an object of such substantial proportions to accumulate enough building material. A more compelling narrative suggests a dramatic migration. Eris may have originated much closer to the Sun, in a denser region near the orbit of Neptune. There, it could have grown to a significant size before the gravitational chaos of the early solar system hurled it outward. Neptune's migrating gravity could have acted like a cosmic slingshot, flinging Eris onto its present, wildly eccentric orbit, depositing it in the scattered disk, a population of icy bodies with similarly stretched-out paths. This would make Eris a captured object, not from another star, but from a different neighborhood within our own solar system. The most radical possibility is that Eris is an interstellar interloper. In the Sun's infancy, it was born in a dense cluster of stars. A close pass by another star could have ripped Eris from its original system, leaving it to be captured by our Sun's gravity. How could we ever know? The key may be in chemical fingerprints. If Eris formed in the Kuiper belt, its composition of ices and rock should match that of its smaller neighbors. If it migrated from nearer to Neptune, its ice might show a different ratio of isotopes, a subtle signature of a warmer birthplace. And if it is truly from another star, its fundamental chemistry could be completely alien, unlike anything else we see in our cosmic backyard. Eris does not easily give up its birth certificate. Its origin remains a cosmic whodunit, with its own orbit and composition as the primary suspects. The search for rings around Eris turns our gaze to the empty space surrounding the world itself. After the stunning discovery of a ring system around the dwarf planet Haumea, astronomers immediately began to wonder if Eris, another giant of the Kuiper belt, might also be encircled by a hidden halo of debris. Detecting such a feature from Earth is a feat of extreme precision, relying on a celestial event called an occultation. Scientists patiently wait for Eris to pass directly in front of a distant star. As it does, they carefully monitor the star's light. If a ring system exists, the starlight would flicker or dim twice, first as the rings block the light, and then again as the main body of Eris itself passes by. These subtle dips in brightness are the only signals that could betray the presence of ethereal rings. So far, no conclusive evidence has been found, but the search continues with every new occultation opportunity. The presence or absence of rings would tell a dramatic story about Eris's past. Rings around such distant objects are thought to be the aftermath of a violent collision. If Eris does have rings, it would be direct proof of a cataclysmic impact in its recent history, a shattering event that blasted material into orbit. This would perfectly explain the existence of its large moon Dysnomia, suggesting a single, ancient crash created both the moon and a potential ring system. If, however, repeated observations confirm no rings are present, the narrative shifts. It could mean that any rings it once had have since coalesced into smaller, unseen moons, or that the impact which formed Dysnomia was a clean, direct hit that did not generate a disk of debris. The void around Eris is not empty of answers. It is simply waiting for the right moment to reveal whether this distant world wears a crown of ice and dust. The apparent youth of its surface stands as one of the most visually compelling mysteries. When we look at worlds like our Moon or Mercury, we see faces scarred by countless impact craters, a historical record of billions of years of cosmic bombardment. Eris, however, presents a different picture entirely. The limited data we have suggests a startling lack of visible craters. Its face is smooth, a gleaming, almost unblemished expanse of ice. This is deeply puzzling because in the chaotic early solar system, the Kuiper belt was a shooting gallery, and Eris should have been pummeled just like every other object. A surface with few craters is a surface that has been erased and rewritten, a clear sign of geological youth. So what force is actively erasing the evidence of these ancient impacts? The answer points toward relentless internal activity. Imagine a vast, slushy ocean of water and ammonia slowly churning deep beneath the frozen crust. This convective motion could be constantly turning over the surface, much like a lava lamp slowly cycles its blobs. As warmer material rises, it pushes the old, cratered crust aside, spreading a fresh, gleaming layer of ice across the global landscape. Alternatively, the process of cryovolcanism could be at work, with icy lavas periodically oozing out to flood vast basins and bury the past under miles of new frost. Each eruption would be a reset button, wiping the geological slate clean. But this activity requires a powerful and enduring source of internal heat. The slow decay of radioactive elements in its core might provide just enough warmth to keep this engine running, even after billions of years. This transforms our view of Eris from a frozen relic into a world that might still be changing today. Is it possible that right now, as we look toward the heavens, this distant dwarf is subtly shifting its own skin, actively concealing its oldest wounds beneath a veil of brilliant, newborn ice? Even the temperature of Eris behaves in a way that defies simple logic. Astronomers measure a property called thermal inertia, which is essentially how quickly a surface heats up and cools down. A world with high thermal inertia, like one covered in solid rock, takes a long time to warm in the sun and a long time to cool in the dark. Eris, however, reveals a surprisingly low thermal inertia. Its surface temperature fluctuates rapidly, responding with unexpected speed to the tiny amounts of solar energy it receives. This is a profound anomaly for a world we assume is covered in solid ice. Solid ice should act like a thermal buffer, holding onto heat and releasing it slowly. So what does this rapid temperature change actually mean? It points to a surface that is not a solid sheet, but an extraordinary layer of incredibly fine, porous material. Imagine walking on a vast beach of frozen, powdery snow that has never been compacted. This is not the hard, packed ice of a skating rink. It is a fragile, frothy layer of frost, a cosmic whisper of a landscape. The low thermal inertia suggests Eris could be blanketed in a foam-like crust of nitrogen and methane ice, a material so fluffy and full of empty space that it has almost no ability to retain heat. When the faint sunlight touches it, the very top layer warms almost instantly, but that warmth cannot penetrate deeper because the material is such a poor conductor. Then, when the world rotates into darkness, the heat radiates away into space just as quickly, leaving the surface in a state of extreme cold again. This exotic, porous surface could also explain the planet's extreme brightness. All those tiny air pockets and crystal facets within the frost would scatter light in every direction, acting like countless microscopic mirrors and creating that brilliant reflectivity we observe. This thermal behavior paints a picture of a world with a surface as delicate and ethereal as frost on a window pane, a landscape that might crumble to dust under the lightest touch. This fragile, frozen crust might be the only thing separating us from the most profound mystery of all. Deep beneath that brilliant, reflective surface, trapped under miles of solid ice, Eris could be hiding a global ocean of liquid water. The very internal heat that powers its geological renewal and cryovolcanism might also be maintaining a dark, abyssal sea, completely isolated from the universe above. For life, as we understand it to exist, two fundamental ingredients are required: liquid water and a source of energy. On Eris, the water would be provided by the heat from its radioactive core, preventing the deep ice from completely freezing solid. The energy would not come from the distant, feeble sun, but from the same slow decay of radioactive elements, or perhaps from the gravitational flexing caused by its moon Dysnomia. This is not a sunlit reef, but a world of perpetual darkness under immense pressure, and yet we know such environments can exist. Look at moons like Europa orbiting Jupiter or Enceladus circling Saturn. Both are small, icy worlds with strong evidence for subsurface oceans, and Enceladus even shoots plumes of its ocean water into space from giant cracks near its south pole. Eris presents a more extreme version of this same tantalizing possibility. It is far colder and more distant, but its substantial mass and density suggest a rocky core that could be rich in the radioactive elements needed to provide warmth for billions of years. Could simple, microbial life cling to a hydrothermal vent on the seafloor of Eris, thriving in the total blackness, fed by chemical energy from the world's core? It is an incredible long shot, a whisper of a chance in the frozen silence, Yet the mere possibility transforms this distant speck of light from a simple curiosity into a potential sanctuary, a hidden bottle in the cosmic ocean carrying the most precious message of all. That debate over Pluto's fate was not a quiet academic discussion. It was a public and deeply personal reckoning for our solar system. The discovery of Eris forced the International Astronomical Union to draw a line in the cosmic sand, creating the first official definition of a planet in 2006. The new rules were stark. To be a planet, a world must orbit the Sun, be round from its own gravity, and it must have cleared its orbital neighborhood of other significant debris. Pluto, and by extension Eris, failed this third test spectacularly. They reside in the crowded Kuiper belt, surrounded by countless other icy bodies. For the IOU, this was a necessary step toward scientific clarity. But for many planetary scientists and a captivated public, it felt like a demotion based on a technicality. The backlash was immediate and fierce. Leading scientists like Alan Stern, the principal investigator of the New Horizons mission to Pluto, argued that the definition was fundamentally flawed. He famously called it absurd, pointing out that by this strict standard, even Earth would not qualify as a planet if it were placed in the Kuiper belt, since it too would be sharing its orbit with thousands of asteroids. The definition, critics argued, was not about the intrinsic nature of a world, but about its location, a cosmic zoning law that seemed arbitrary to many. The emotional connection to Pluto ran deep, fueled by childhood mnemonics and a cultural attachment to the little world at the edge of every textbook diagram. This was not just science, it was a battle over how we categorize our cosmic home and what stories we tell about it. The debate raged in conference halls, on newspaper op-ed pages, and across dinner tables, proving that how we define a world can be just as contentious as the world itself. And at the center of that storm was the distant, silent trigger, Eris, a world whose very existence had forced us to question what we thought we knew. The name Eris was a prophecy written in the stars long before we knew its target. In Greek mythology, Eris was the goddess of strife and discord, the divine instigator who tossed the golden apple inscribed for the fairest into a wedding, an act that ignited the Trojan War. When astronomers bestowed this name upon the distant, bright object discovered in 2005, they could not have chosen a more fitting title. The public, captivated by the idea of a 10th planet, immediately embraced this new world, but the name Eris proved to be a perfect mirror for the upheaval it would cause. It was not just a new discovery, it was a celestial agent of chaos that forced a painful but necessary redefinition of our cosmic family. The mythology that grew around it was powerful, framing this icy sphere as a rebel that had stormed the gates of planetary science. People saw a cosmic irony in the fact that the goddess of discord had single-handedly turned the ordered solar system of our textbooks into a battleground of definitions. This public narrative transformed Eris from a scientific datum into a cultural icon, a symbol of challenging the established order. How many other objects, hidden in the dark, hold the potential to rewrite the stories we tell ourselves about the universe? Even its steady glow holds a secret flicker. Astronomers monitoring Eris have detected small, unexplained changes in its brightness over time, subtle shifts that cannot be accounted for by its simple rotation. If its surface were a uniform, static shell of ice, its light curve would be predictable and regular, but it is not. These photometric variations are tiny anomalies, whispers of something more complex happening on or around this distant world. One possibility is that the surface itself is active. Imagine vast plumes of volatile gases erupting from beneath the ice, freezing instantly into brilliant clouds of fine crystals that drift above the landscape. These temporary hazes would scatter sunlight differently than the solid ground below, creating a faint, global dimming or brightening as they form and dissipate. Alternatively, the surface composition might be changing in real time. Patches of darker tholins could be exposed by shifting ice, only to be covered again by fresh, white frosts, each event slightly altering the total amount of light Eris reflects back to us. Perhaps the most intriguing explanation involves unseen actors. Dysnomia is its only known moon, but what if a family of smaller, undetected moons orbits Eris? These tiny, dark companions would be impossible to see directly from Earth, but their presence could be betrayed by their shadows. As they pass in front of Eris from our perspective, they would cast tiny, moving dots of darkness onto its brilliant surface, causing brief, precise dips in its luminosity. Each flicker in the light of Eris is a potential clue, a coded message from the deep that the story of this dwarf planet is still being written, its surface and surroundings far from inert. All these clues lead to a single, profound conclusion about what lies beneath the surface. The true nature of Eris is locked within the puzzle of its density, a number calculated from its mass and its estimated size. We know it is massive, we know it is small, and when you combine those two facts, you find that Eris is astonishingly dense. This is not a loosely packed snowball. It is a compact, heavy world. For an object in the distant Kuiper belt, which is supposed to be a realm of fluffy, icy conglomerates, this high density is a major surprise. It forces a dramatic rethinking of its internal architecture. The most compelling explanation is that Eris is a differentiated world, meaning it has separated into distinct layers, much like Earth. At its heart likely sits an enormous, rocky core, a sphere of silicate rock and metal that contains most of its formidable mass. Enveloping this core is a thick mantle of water ice, and above that, the thin, brilliant crust of frozen methane and nitrogen we observe. This layered structure tells a story of a violent, energetic youth. Differentiation is not a passive process. It requires intense heat, enough to melt the interior of a planetesimal so that the heavy materials like rock and metal can sink to the center while the lighter ices float upward. This means that in its early history, Eris was a molten, seething world. The heat could have come from the energy of its own violent formation, as countless smaller bodies smashed together to build it, or from the fierce and rapid decay of radioactive elements like aluminum-26, which was abundant in the early solar system. This hidden, rocky heart is the engine that may still drive its geology today. Its radioactive decay providing the gentle, persistent warmth that could power cryovolcanism and maintain a potential subsurface ocean. Eris is not a simple ice ball. It is a world with a geological soul, a complex sphere of rock and ice whose internal fire defies the frozen silence of its orbit. Reaching out to touch this distant world is a voyage of almost incomprehensible scale. A spacecraft launched toward Eris today would not arrive for decades, a journey spanning a human lifetime. The sheer distance creates a fundamental problem of energy. To reach the outer solar system quickly, a probe needs immense speed, but then it must slow down upon arrival to enter orbit, a maneuver that requires even more fuel. With current rocket technology, such a mission is a monumental challenge. Imagine a robotic explorer, a descendant of probes like New Horizons that flew past Pluto, but designed for an even longer and more isolated trek. It would likely need a nuclear power source, as solar panels are useless so far from the sun's light, and it would carry a sophisticated suite of instruments. Its primary mission would be to answer the questions we can only guess at from here. It would map the entire surface in stunning detail, searching for the telltale signs of cryovolcanism, fresh ice flows, and the faint patterns that reveal a subsurface ocean. It would analyze the composition of that brilliant surface, sniffing the thin seasonal atmosphere to determine its exact chemical makeup. And it would study Dysnomia up close, determining its density and structure to finally unlock the secrets of the Eris system's violent birth. The scientific bounty would be immeasurable, rewriting our understanding of these frozen frontier worlds. Yet the greatest challenge is not just engineering, it is patience. The scientists who design such a mission today might not live to see its triumphant arrival, a testament to the human drive for discovery that spans generations. What breathtaking vistas would its cameras finally reveal? And what new mysteries would we find waiting on that gleaming, frozen shore? The gravitational echoes of Neptune's grand migration still ripple across the solar system today. Billions of years ago, in the chaotic dawn of our planetary family, the giant planets are believed to have shifted their positions. Neptune, in particular, is thought to have slowly drifted outward from a birthplace closer to the Sun. As it migrated, its immense gravity acted like a cosmic plow, shepherding and scattering a vast population of icy leftovers from the solar system's formation. Eris, with its wildly tilted and elongated orbit, is a prime candidate for being one of these scattered objects. It was likely not born in its current, lonely exile, but was instead hurled there by a gravitational kick from the drifting Neptune. Scientists use sophisticated computer simulations, called dynamical models, to rewind the solar system's clock. They input the current orbits of Eris and other Kuiper belt objects, then run the simulation backwards in time, factoring in the gravitational tugs from all the planets. These models consistently point to a dramatic past. They suggest Eris was once part of a denser, more sedate population nearer to Neptune. The planet's outward journey created a gravitational resonance, a repeating tug that pumped energy into Eris's orbit over millions of years. Like a child being pushed higher and higher on a swing, Eris was gradually swung into an ever more stretched-out path, until finally it was ejected into the scattered disk, the desolate region it inhabits today. This theory elegantly explains its strange trajectory, but a critical puzzle remains. The sheer degree of Eris's orbital tilt is difficult for some models to replicate perfectly. This suggests its journey may have been even more violent, perhaps involving a close encounter with another large, since vanished planetary body. The ghost of Neptune's migration is written in the path of Eris, a fossilized record of the solar system's most turbulent era. The slow dance of its orbit means a single season on Eris lasts for well over a century. We are forced to imagine a world where the concept of a year loses all human meaning, a cycle of change so glacial that civilizations could rise and fall between its spring and its summer. The most dramatic transformation occurs during its fleeting perihelion, the point where it makes its closest approach to the Sun. For a brief window of perhaps a few decades, the feeble sunlight intensifies from a distant pinprick to a marginally stronger star. This minuscule change in solar energy could be enough to trigger a global upheaval. The nitrogen ice that forms its brilliant crust begins to warm, not enough to melt, but enough to sublimate, turning directly from a solid into a gas. A temporary atmosphere, wispy and tenuous, puffs into existence around the frozen world. This would not be a sky as we know it, but a low-lying haze of nitrogen and methane vapor, a fragile shroud that might last for a generation before the world's journey back into the deep freeze begins. As Eris recedes on its 557-year trek, this temporary atmosphere would not simply vanish, it would undergo a spectacular collapse. The gases would refreeze, falling back to the surface as a fresh layer of crystalline frost, snowing out of the sky to blanket the landscape in a new coat of pristine white. This cyclical process of exhalation and freezing could be the very mechanism that constantly renews its mirror-like surface, scrubbing away the dark, ancient stains of radiation and impact. The Eris we see today, dazzling and bright, might simply be caught in a particular phase of this epic seasonal cycle. What would its surface look like at the opposite extreme, at its most distant and coldest point? It might be a far more complex and mottled world, with ancient, darkened terrain peeking through where the frosts have retreated. We are witnessing only a single, frozen frame from a movie that spans centuries, leaving us to wonder what breathtaking scenes are playing out in the acts we cannot see. This slow celestial dance is not set in stone for all eternity. The ultimate fate of Eris is written in the subtle, relentless pull of gravity from the giant planets, a force that tugs at its orbit over eons. While its path seems stable for now, the solar system is a dynamic and unpredictable place. Over the next billion years, the cumulative effect of countless tiny gravitational nudges, especially from Neptune, could fundamentally alter its trajectory. One possibility is a gradual stabilization, where these interactions slowly circularize its orbit, locking it into a more permanent and predictable loop in the outer darkness. But there exists a far more dramatic destiny. A particularly close gravitational encounter could act as a cosmic slingshot, accelerating Eris to escape velocity. In this scenario, the Sun's gravity would simply lose its grip. Eris would break free from our solar system entirely, becoming a true interstellar object, a lone wanderer drifting between the stars for eternity. It would join the vast population of rogue planets and planetesimals that are now believed to outnumber the stars in our galaxy. Alternatively, its path could be perturbed inward, sending it on a long, slow fall toward the inner solar system. Over millions of years, it could evolve into a new kind of object, a giant centaur with a spectacular, developing tail as its ices vaporize in the sun's growing heat, or even face a catastrophic collision with one of the planets. Its current existence is merely a snapshot in a much longer, epic journey. The forces that shaped its past are still at work, quietly determining whether this distant world will remain a part of our cosmic family or become a permanent exile, carrying its frozen secrets into the boundless void between the stars. Eris stands as a collection of cosmic contradictions, a world where every answer seems to generate two new questions. From the fundamental uncertainty of its own size that reshaped our solar system, to its impossibly brilliant and youthful surface, this distant dwarf planet defies simple explanation. Its potential for a transient atmosphere, the mysterious nature of its large moon Dysnomia, and its wildly eccentric orbit all point to a violent and dynamic history. The possibility of a hidden subsurface ocean, powered by a radioactive heart, suggests a world that is geologically alive against all odds. Its strange thermal behavior, the puzzle of its persistent methane, and the faint, unexplained flickers in its light all whisper of active processes we have only begun to decipher. The very definition of a planet was forged in the fire of its discovery, a debate that continues to resonate through science and culture. Eris challenges our assumptions at every turn, forcing us to reconsider what we know about the formation, evolution, and potential for activity in the frozen reaches of our cosmic neighborhood. It is more than just a dwarf planet. It is a key to understanding the chaotic infancy of our solar system and the hidden potential of icy worlds. What do you think is the most compelling mystery of Eris? Could its dark, subsurface sea hold secrets we have not yet dared to dream? Share your own theories in the comments below, and subscribe to continue exploring the deepest enigmas of space.